Welcome to the second part of our tutorial wherein we will be proving statements whether they are tautologous, contradictory, or contingent statements. First, we must define what are these statements. A tautologous statement is a statement which always results in true or always has a value of 1. A contradictory statement always results in false or has a value of 0. A contingent statement is neither a tautology nor a contradiction, which means that it can have a value of 0 or 1. There are two methods of proving logical statements. First is by using the truth table method, wherein we could use the different truth tables of the different logical connectives to arrive at a certain solution. Next is by using replacement rules. These are different postulates and theorems that would help us arrive at a certain answer without the use of truth tables. For example, we have this problem. Prove that P or not P is a tautology. First, we must find out how many variables are used. There are only one variable, which is P. Next, we need to break down the components of the statement into a simpler one. We must first get the negation of P before proceeding to the disjunction of P and its negation. So first we must provide the possible values of P, which is 0 or 1. When we negate P, as shown in the negation truth table, if P is 1, the negation is 0, and if P is 0, the negation is 1. So if P is 0, its negation will be 1. If P is 1, its negation will be 0. And the conjunction of 0 or 1 and 1 or 0 is equivalent to 1. Since this part always results in 1, we could therefore conclude that P or not P is a tautology. Next example of using truth table method is P and not P and P and P. We must break down the statement into components so that we could analyze the resulting truth table values of each, with the negation of P, the conjunction of P and not P, the conjunction of P with itself, and the conjunction of the previous propositions. We now provide the possible values of P, which is 0 and 1. The negation of 0 is equal to 1. The negation of 1 is equal to 0. The conjunction of these two columns will be equal to 0, 0. The conjunction of P with itself, 0 and 0 is equal to 0. 1 and 1 is equal to 1. Lastly, the conjunction of these two columns, 0 and 0 is equal to 0. 0 and 1 is equal to 0. Therefore, this statement is contradictory because the resulting value is always 0 or false. Another use of the truth table method is to determine whether two statements are logically equivalent. For example, show that not P or Q and not P and not Q are logically equivalent. First, we must determine the truth table of the first statement. We must provide the possible values of P and Q. P is 0, Q is 0. P is 0, Q will be 1. 1, 0, and 1, 1. We would then evaluate the inner expression. P or Q, which means 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. And finally, we would then negate the answer from the previous column. Negation of 0 is equal to 1. Negation of 1 is equal to 0. The next step is to provide the truth table for the next statement. First, we must provide the possible values for P and Q. We would then negate the P as well as the proposition Q. We would finally conjunct the previous two statements or the negations. 1 and 1 is equal to 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0. To check if the two statements are logically equivalent, we must go see the last column of their truth tables. Since they are equal, we could conclude that the two statements are logically equivalent. The next method is proving using replacement rules. First, we must enumerate the different replacement rules. Commutative, wherein P and Q is equal to Q and P. P or Q is equal to Q or P. Associative, P or Q or R is equal to P or Q or R. P and Q and R is equal to P and Q and R with different groupings. Distributive, P and Q and R is equal to P or Q and Q or R. P and Q or R is equal to P and Q or P and R. De Morgan's law. Not P and Q is equal to not P or not Q. Not P or Q is equal to not P and not Q. Double negation. Not P is equal to P. Material implication. P implies Q is equal to not P or Q. Material equivalence. P if and only if Q is equal to P implies Q and Q implies P. P if and only if Q is also equal to P implies Q or not P and not Q. Tautology. P or P is equal to P. P and P is equal to P. P or not P is equal to true. P and not P is equal to false. Domination. P or true is equal to true. P and false is equal to false. Lastly, the identity. P and true is equal to P. P or false is equal to P. Let us have an example proving using replacement rules. The problem is show that P implies Q and P implies Q is a tautology. We all know that a tautologous statement results in a true value. First, we must remove all the implication operator through material implication. Since material implication states this rule, P implies Q be equal to not P or Q. Let us have this part of the statement as the variable P. So this would be the one that would be negated and the implication operator would be removed. Next, we remove the next implication operator. Since there are negations outside the parentheses, we'd have to use De Morgan's law. By distributing this negation over these two propositions, we would change the operator N into OR, and the negation would be distributed. Next is by using De Morgan's law again, because there are still negations outside the parentheses. The OR operation here would be converted to N, and the NOT or negation would be distributed to the two propositions. Since there are two negations overlapping each other, we would cancel this using the double negation rule. The statement would be P and not Q or not P or Q. We would then use the commutative to follow the form of the distributive. In order to use distributive, we must have this form, P or Q and R. Since the format of the statement inside the parenthesis is not the same as the format in the distributive law, we must commute first the statements before we distribute them. Again, the inner part of the statement in this parenthesis would comprise and correspond to one of the law of our replacement rules, which is the negation. P or not P is equal to true. True and not P and not Q or Q. We would again use another replacement rule because true and another variable, we would take these statements as one variable. So true and another variable, according to our identity rule, is equal to the variable itself. So in this part, we remove the true value. The remaining would be not P or not Q or Q. We would then again use another replacement rule. Since the operators are the same inside and outside the parentheses, we could change the grouping of it. We change the grouping to not P or to the group of not Q or Q. Since this has another replacement rule which is equal to P or not P or Q or not Q is equal to true, through negation we will change it into a true value. Not P or true. As we go look into our replacement rules, not P or true, or we could say that not P will become the variable P. P or true will be equal to true through the domination. Therefore, the statement is a tautology.